So my talk today is called An Origin Story. I work as a principal software engineer for the BBC, and I've been there for about 10 years now. But before that, for about 20 years in industry, so another 10 years on top of that. Excuse me. And I've been writing code for about 20 years. So my team in the BBC is media services. And we're responsible for publishing all the BBC's online video content for iPlayer, BBC Sounds, News and Sport. And we handle live content, catch-up, podcasts, that kind of thing. And every day we ingest and publish over 1,000 hours of catch-up content. We publish 3 to 4 terabytes of new files, and we handle 13 million play events. And actually, these are quite low numbers as well. We need to look at some fresh numbers to see actually how this has grown, because it's definitely grown over time. So in terms of Go, I would say I'm a relative newcomer with about a year's experience. But as soon as I met Go, I knew it was what I'd been looking for. But it wasn't just that Go was new and shiny. And I've been writing code for a fair while now, and as soon as I started working with Go, a huge amount of the frustrations I've found with other languages simply didn't exist anymore. So this talk is about some of those things that I discovered when learning Go, mostly from other people who know Go really well. So it's kind of a summary of their experiences, if you like. And it also probably contains my opinions. You can do with that what you choose. So this talk is about Go's origin story and why it's developed the superpowers that it has now. So we'll go through where Go comes from, the ideas that formed Go, what Go became, and we'll look at some code which shows some of the ideas in action. So let's look at the world before Go, if we can transport ourselves back in time. If we think back to the early days of computing, programming languages came with the hardware you bought, and each manufacturer of each piece of hardware would supply a new programming language with every model of computer. And since then, a huge number of languages has appeared. And this is a chart of programming languages from Digibarn, and it dates from 2001, and it tracks from Fortran up to the current time then, in 2001, when they were tracking at the time 2,300 languages, and there's a huge amount more now. So why create yet another programming language? I think the answer comes by looking at the type of environment from which Go was born. So in the early 2000s, server rooms looked quite like this. There was lots of on-prem infrastructure, and it could be said that programming languages at the time reflected this kind of pattern, or this kind of organization. There was a move to platform portability, and from the desire to avoid having to write code for every single different platform came things like the Java virtual machine, an abstraction on top of an operating system which would allow the same code, with some caveats like the Java native interface, to run on any platform. Any platform, at least, that supports a JVM, and it also benefits from things like garbage collection. However, anybody that's managed infrastructure requiring different Java runtime versions will agree that it can be really complex to manage. And also building Java applications themselves, they're slow, and it generally requires third-party tools such as Maven. And building C++ projects as well, they can be rather onerous. And while you can result in a performant executable targeted for a particular platform, the process for building that binary can be exceptionally slow, in part because the project might require many header files to be loaded and compiled, and each one typically has to be compiled because of variations caused by macros that can actually change the content of these header files. And when compiled, the resulting set of object files need to be linked together in a largely monolithic process, which can't be parallelized very easily. Of course, C code shares many of the same features, but it's a lot less onerous to parse. Parsing C++ code can take significantly more time. And also, especially when you're using templates, which are a feature of C++ that allows functions and classes to operate with more generic types. So often programming languages force you to make a decision. We could have efficient compilation, such as with C, efficient execution, or ease of programming, arguably with Java and garbage collection. But from experience, Java projects are not at all efficient to compile, even using tooling that uses partially built checkpoints to speed builds up. And this situation remained until this gentleman, I'm sure lots of you recognize, until about 2007. And Rob Pike here was, at the time, a member of the C++ committee. And C++ is what you might describe as a fully featured language. And during a meeting to talk about yet more new features of C++ 11, Rob asked himself, did the C++ committee really believe that what was wrong with C++ is it didn't have enough features? Surely, he said, it'd be a greater achievement to simplify the language rather than add things to it. Another time, Rob shared an office with Ken Thompson on the right. He is a legend, I'm sure lots of you all know, who designed and implemented the original Unix operating system. He invented the B programming language, which is the predecessor of C. He also shared an office with Robert Grissommer on the left, who had previously worked on the V8 JavaScript engine and the Java hotspot virtual machine. So you can start to see this kind of pedigree of the team in the early days. And on the 21st of September 2007, during one of their 45-minute long C++ builds, they began to work out what a new language could look like. And the conversation coincided with a wider move to the cloud, where a different approach in resiliency and stability was much more important. And earlier on, one of the big decisions they made was it should be a language that accepts and deals with failures, rather than them being considered exceptions, such as in a language such as Java. And it's reflected in a new way of thinking about infrastructure and software generally, rather than trying to prevent failures. Instead, accept that they will happen and then deal with them accordingly. In fact, Google's first VP of engineering, Urs Hotzel, spoke of this as at scale, everything breaks no matter what you do. You could say, yeah, but we're not Google. Well, it's true, but we still want resilient and available systems without spending more money than we need to. And Google may have thought this way at first, but we all benefit from this thinking, especially in the cloud. Because, of course, this is what our server room looks like now. And it might not be our own, but this is where our code runs in multi-tenanted, highly available data centers. But the original intention of Go wasn't just to scale into the cloud computing into data centers, but more importantly, to scale as development teams grow. And to ensure Go scaled with development teams, the language itself was to be simple. Simple may mean that you can add every single feature to it so you can solve every single possible problem you may ever face, or make it simple such that people can create straightforward and readable code. In fact, Tony Hoare, the computer science hero, I'm sure people recognize him, the developer of Quicksort, you've certainly used his code anyway, or his algorithm. He mentioned that you can either make software simple with obviously no deficiencies, or so complicated there are no obvious deficiencies. And Go then, okay, so it needs to be simple, but what actually should it be? So Go formed around these three kind of important features. It must be simple, it must be readable, and you need to be productive both with large, mature systems and brand new code bases. And this is what the Go team meant when they said the language must scale. Note that we didn't say performance or concurrency or a complete library, but fast to get started in and fast to be productive in. Instead of having to learn a huge language spec, Go spec is relatively small and concise. Go is also fast. But I think fast means different things to different people. In terms of compute, Go is intended to be performant, but there's probably some confusion about what fast actually means in the wider context. So I'm going to paraphrase a few people here and add a bit of my own. But as a rule, choosing a programming language based on raw performance is almost always the wrong thing to do. If we consider the earlier trade-offs that we were discussing, we could write some extremely fast code in a low-level language, but we'd lose the ease of programming. For example, x86 assembly, I would argue it's fast language, but we would lose that ease of programming. It's kind of demonstrated in this Hello World example here. So when we say it's fast, we could be talking about raw compute speed, although the more important definitions of fast are productivity and the tools to build a large executable on a single computer in at most a few seconds, reducing that build cycle overhead. So these ideas began to coalesce into a programming language. And in this email from 2007, Rob Pike gave Go its name. As a side note, Golang is a website, and also a term when we can use to look up stuff on Stack Overflow, and Go is the language. So the Go team decided on some design principles, that most ideas come from previous ideas. The new languages should consolidate and not invent new features. It should have a consensus-driven design, And it should expect and enable massive changes. And by this means generally as well in our teams as well, as we experience change in our organizations, change in our teams, and huge amounts of refactoring. So as an example of ideas coming from previous ideas, one of the lessons learned in Go was that there's no type hierarchy. Types just are. And to understand what this is, you need to look at a language like C++ or Java, in which you might end up with a hierarchy such as this. It seems simple at first, but it can soon get out of hand, especially when you consider the complexity at the top of this hierarchy affects objects lower down, as every child inherits their parents' features. And it means you're passing on attributes you may not require to lower implementations, so your classes start to become bloated with all this baggage from their parents. And once that's happened, it's really hard to refactor that away. The Go language designers consider this type of model to be brittle, and I entirely agree. In fact, the inventor of Java, James Gosling, during a Java user group meeting, was asked, if you could do Java all over again, what would you change? And he replied, I'd leave out classes. But he explained the real problem wasn't classes per se, but rather implementation inheritance, the extends relationship. Interface inheritance or implements relationship is preferable. But we'll look later on at how Go deals with the absence of classes and why it intended to not have classes. So one of the issues with the implementation inheritance we were talking about is this diamond problem. It's an ambiguity arises when two classes B and C shown here inherit from A. Then class D inherits from both B and C. The ambiguity is that if D inherits a method, which method does it get? From B or from C? And this is some of the reasons why some languages support only single inheritance. Of course, there are alternatives to implementation inheritance in other languages, and one of those is composition. And Go makes it easy to think in terms of composition, as Java makes it easy to think of in terms of inheritance. But this idea of implementation inheritance, the extends relationship, has really influenced, I think, our idea of what object-oriented software design is. In fact, so much so that often inheritance is interchangeable as a term with object-oriented programming. It's certainly the first thing that comes to mind to a lot of people. The term object-oriented was actually coined about Smalltalk, and it's helpful to consider what it meant then. Alan Kay here, who led the Smalltalk team, explained the term object-oriented underemphasized the more important idea of message sending. Go's object-oriented approach is influenced by this idea of message sending and this idea from Smalltalk. So we've seen that Go is an object-oriented language. It supports message sending on any type, and it uses interfaces. So looking at where Go has come from, the ideas that underpin the language, the lessons learned from the past, we can see this reflected straight through the Go programming language itself. So let's look at some code. So as in Smalltalk message sending, Go has methods which provide message sending on any type. An example, I work for the BBC, so imagine you want to write some code to manage scores on Strictly Come Dancing. So we declare a type, Strictly Scores, which is a slice of integers, and they'll track our scores in a round. As we want to print these scores, a method string is added to the Strictly Scores type. And the function is implemented, in this case a simple thing, just to concatenate integers into a string and return that. So now we can call the string method on our Strictly Scores, or indirectly call it with something like funct.println. So it's great, we can add methods to a type. We talked earlier on about interfaces, and Go uses them to provide reusability using dynamic dispatch, the process of selecting which implementation of an operation, method or function, to call at runtime. So now we want to implement a print function to print our score string. We could pass in our Strictly Scores type, although then we'd need to implement a print function for every single different type we might have. And maybe we want to reuse the functionality in that print method with different types. So instead, an approach is to use an interface, define an interface called displayer. And this is using the Go convention of a something. The displayer interface defines any methods that any implementation will need to implement to become a displayer, string in our case. And we implement a print method which accepts any displayer. Previously, we defined a method called string on our strictly scores type, but as interfaces in Go are implicit, we don't need to change any of this code at all. Unlike a language like Java, in which we'd now need to go back and update the code to implement this new interface. Instead, strictly scores already implements this method defined in our displayer, and so it already satisfies this interface. And now our strictly scores, because it implements this displayer interface, we can use it to print our scores. This is an example of Go's separation of data and behavior. The data and behavior are two distinct concepts, not conflated into a single notion of class. And this is another reason why Go doesn't have classes, because of this binding of two separate concepts. So when thinking about the language, earlier on in the design process, some features of Go began to emerge. That it should reduce clutter and complexity. It should have an expressive but lightweight type system. It should support concurrency and have a garbage collector. And it has a rigid dependency specification. And in fact, the joke is that if you could get anything past Rob, then it was in the language, but not many did. That's changed now. The example of reduced clutter is the short variable declaration syntax. So this line here is rather verbose. But with the short variable declaration syntax, that line becomes this, which reduces a lot of boilerplate and that cognitive load you experience when looking at code. And for loops are the only type of loops in Go, but they're extremely powerful. In this example, a for loop is used to create a standard type of for expression on the top, a while type of expression, an infinite loop, and a for each construct. And you probably heard that Go deals with concurrency well. It's one of the big selling points of the language. But by way of a definition, concurrency is about dealing with a lot of things at once. Parallelism, which it sometimes gets confused with, is about doing lots of things at once. Parallelism is about running code on multiple CPUs at the same time. As an aside, this is a really good talk. Some of you might have seen it, and I'll link it up at the end. So to give some context, at the time when Go was developing, concurrency could be approached largely with a couple of main strategies, if you like, threads and events. A thread of execution is the smallest unit of execution that can be managed independently by a scheduler, which is typically part of the operating system itself. For distributed systems scaling, this was an issue, and threads managed in that operating system just don't scale. And to solve the problem, we threw more resources at the problem, and hyperthreading came along for Pentium processors, and that helped out performance, but generally this performance is plateauing, and another approach clearly is needed. But to deal with concurrency also, event-based systems, which use callbacks to deal with concurrent tasks, were developed. This type of model is used in pieces of software like NGINX, which suits HTTP requests, because the requests are received, they're handled, and a response is sent to the caller, largely out of context with other requests. And this is an example. This is the NGINX event loop, which waits for events and processes an events queue. It's quite possible to build your application code within NGINX. You can compile stuff, and it becomes part of that model. You benefit from some performance, but you need to build your application specifically for this platform, if you like. And going back to the earlier point of ease of programming, it's clear that people don't consider this easy, because instead they use NGINX to handle HTTP traffic, and they proxy requests back to an application server running their code somewhere else. For this reason, often web servers are configured to forward to application servers like Apache Tomcat. So we're not benefiting from that event loop. And in fact, that kind of traffic, it's stateless traffic, which it handles particularly well. The event loop model is used in Node.js, as I'm sure many of you all know, where requests are serviced by an event loop, which registers and triggers callbacks. An event loop essentially is a continual hamster wheel of computation being scheduled and callbacks being executed. And Node.js uses a single-threaded event loop model, which in a multi-threaded server can mean that resources are managed using inter-thread communication, which can affect performance, especially if you need to scale out to a huge scale. So it's true that stateless threads can be performant, as in NGINX's events loop with HTTP traffic, but when we start to require coordination between threads, that's when our performance begins to degrade. So Go's approach to concurrency is influenced by Tony Hoare's 1978 seminal paper, Communicating Sequential Processes, which is a good read if you can get through it. It took me a while to get through it. And this approach has no sharing of memory, it has no mutexes, no threads, and it describes how each unit of execution runs as if a separate, singly threaded program and how these processes communicate. And this is a big influence on the nascent approach in Go. So this type of communication in Go is in part provided by channels, a typed conduit through which you can send and receive values. And Go has a set of proverbs you might have come across as well. They're kind of well-known pithy sayings which state a general truth or piece of advice. And one of these is to don't communicate by sharing memory, share memory by communicating. And by way of an example of this, this code polls a list of URLs using a traditional threaded approach, which uses a lock mutex. Now, you probably can't see that code because it's purposely quite small, because looking at this alternative implementation using a Go idiom, this function receives resources to be polled from an input channel. It then sends them to an output channel when they're done polling, making the code much more simple. And I would suggest even more performant too, because the code's understandable. You can look at the scope of the code. It's not to say that mutexes don't have a place, but they're fine-grained and they tend to serialize execution. Again, one of the Go proverbs, channels orchestrate and mutexes serialize. And Go, in another part, provides Go routines, which allow functions or methods to be run concurrently with other functions and methods. They're analogous to very lightweight threads. The thread types you would have heard of as probably as green threads. They're threads that are scheduled by the runtime, the Go runtime, instead of by the underlying operating system. The problem is when you're using threads is the stack size needs to be specified and it's fixed. Go routines are only a few kilobytes in size, and the stack can resize according to application requirements. So these lightweight Go routines are multiplexed onto a smaller number of threads overall. And if any Go routine in one thread blocks, another thread can be created, and the remaining Go routines can be shifted onto this new thread. And all of this is handled for us by the Go runtime. So our code can use Go routines by adding the Go prefix. So taking this code and adding the Go keyword. However, in this example, our greet function at the top will run concurrently with the main execution. So it may still be running when our program terminates. So we might need to wait for it to execute, or for a return value, for example. So this code, it creates a channel to inform us when we're done, although we could pass a more meaningful value, some sort of result. And our greeting is run using a Go routine, and then we wait for the routine to complete before beginning. So putting Go routines and channels together makes for a very powerful approach in managing this concurrency. So another feature of Go is that it has garbage collection, much like the Java JVM. And this is again managed by the runtime. In 2015, an announcement on the Go blog introduced a new concurrent tricolor mark sweep garbage collector. Again, this isn't a new idea. It's one first proposed by Edsger Dijkstra in 1978. In Go's tricolor collector, every object that's been created by our code is marked either white, grey, or black, and the heap is viewed as a graph of connected objects. At the start of the garbage collection cycle, all of the objects are marked white. The GC then visits objects which are directly accessible by the application, such as globals and things on the stack, and it colours these grey. The GC then chooses a grey object. It turns it black and then scans it for pointers to other objects, turning those grey also. At this point, the white objects remaining are known to be unreachable, so they can be collected. The cycle then begins again. So you can see this in the visualization of an application benchmark. The garbage collection calls on about the 5th line or something down. And these calls are happening since version 1.8 of Go concurrently, rather than in a stop the world paradigm where everything stops and the garbage is collected. But one of the other performance benefits of the Go language is that structs, there's many more values. Structs are values and there are many more values. In a language such as Java, most types are references, other than some primitives like int and long. And this can put huge pressure on the JVM garbage collector and can require quite a bit of arcane tuning to avoid GC pressure, which is when the garbage collection doesn't keep up with the memory deallocations. Go is also a set of tools. It's not just the language spec, it's not just the libraries. The Go command contains lots of separate tools. Build and run are probably most familiar to most people. The Go build tool itself compiles packages and dependencies, including the Go runtime with that garbage collection, containing an extensive library into every Go program. This runtime library itself implements that garbage collection, it implements that concurrency, stack management, and other critical features of the Go language. But it's important to note, I think, that Go's runtime doesn't include a virtual machine, such as provided by the JVM. Go programs are compiled ahead of time to native machine code, or JavaScript or WebAssembly for some alternative variations. This, I think, is one of Go's most compelling features, that you can compile or cross-compile a native binary which doesn't require an external runtime. For containerized applications such as Docker containers running on container orchestrators, this makes Go a first-class citizen. Another tool you probably use regularly is GoFumt. And it turns something like this code into this code. Apparently, GoFumt doesn't even format code the way that Robert Grissomer formats code, and he wrote the tool. But experienced Go programmers like GoFumt. They may even say they don't like how it formats, but they do like that it does format. And it avoids coding standard wars, which can get pretty ugly. So when you take this heritage, you need to look at the criticisms that people level against Go. Often people say it's nothing new. But if we remember one of Go's design principles, then most ideas come from previous ideas. And Rob's point about being a greater achievement to simplify a language rather than just add more features to it is important to consider here. If somebody tells you, well, it's nothing new, you can say, that's great. Some say it's slow to adopt new features, aka the generics debate. But if something really isn't ready, then it's not included. As Solomon Hykes here puts it, no is temporary, yes is forever. But historically, though, Go dependencies were managed by setting an environment variable GoPath. This contains a path to your code base, which would be used at a point at which code can be compiled, binaries built, and dependencies stored. It was a bit of a pain, I'm sure you'll agree, especially for anything other than the latest version of a dependency. But now we have Go modules. Running Go mod init in your project directory creates a file used to manage dependencies. Another side effect, if you like, of the Go language, that it also uses UTF-8. And this was developed also by Ken Thompson and Rob Pike. And it's a variable length encoding of Unicode code points as bytes. There are over 120,000 characters and well over 100 different languages. And we could represent all of these characters as int32 values. However, ASCII characters only need 1 byte, so it's clear there's a huge waste when using larger precision types. UTF uses between 1 and 4 bytes to represent each symbol. Only 1 byte for ASCII characters, and 2 or 3 bytes for most runes, or they represent Unicode code points. Most runes in common use. So we've gone through the world that Go comes from, the ideas for that foundation of the language spec, the genesis of Go and the code. But of course, Go is much more than just the language, as we've seen. It's the history, the specification, the language, the tools, the runtime, and the standard library. But also it's you, because ultimately programming languages are for people. So I hope this has given a bit of context in this kind of random whistle-stop tour of Go's origin story, and in some way explains that origin and why Go, building on the past, is really a language fit for the future. And if this talk has made you want to study a bit more, then you might be interested in the study group that we meet up once a month, and yeah, you'd be welcome there. Thank you very much. If there's any questions that have appeared.
Anybody have questions there? Can you repeat the question?
Yeah, I'll repeat the question.
Why didn't you mention anything about testing?
The question is, why didn't I mention anything about testing? That's a really good point, just by my own omission. I always like in programming books to read about testing first, and they're always at the end, and I've just done the same thing. So it's a really good point. I think Go's tooling, maybe we can kind of crowbar into the bits on tooling that I mentioned, but Go's tooling out of the box doesn't require extensive toolkits to do your unit testing, to do performance testing, benchmarking, all of these kind of things. That's bound into the tool set that we've got. So yeah, that's my bad. I'm glad you picked me up on it.
Last one.
Yep.
If you could reinvent Go from scratch, what would you change?
That's a really, so the question was, if I could reinvent Go from scratch, what would I change? I think, I'm not sure. I think testing is really important, so maybe a bit more focus on testing out of the box, so as a kind of primitive. Yeah, I don't know. I find that difficult to answer because I'm kind of a bit in awe of the people. I don't think we should necessarily be in awe too much of the people that create these languages, but they did some really special things, and I think by coming together, they brought all these ideas from the industry together. So I think that's something that I really take from Go. It's not just somebody that had an idea and went away and implemented it. They collated together so many different ideas from so many different people. So yeah, I think maybe, I don't know. Yeah, I think that's probably all I can say, but it's a really interesting question. Thanks. Thank you.